Hello, everyone. It's time for a little bit more organic chemistry, specifically about Friedel-Crafts reactions. We're in Key Concepts, Unit 1, Part 3. Let's see. It's this one here. Yep. And so let's see. Last video, we discussed these 8 reactions and then talked about their common mechanism. Okay. So this short video is just going to emphasize some of the problems, some of the limitations of the Friedel-Crafts reactions. The Friedel-Crafts alkylation reaction, where you put an alkane, alkyl group onto benzene, and the limitation where you start with an acid chloride and put the ketone group on the benzene ring. Okay, so darn it, places to watch out for when you're doing your homework problems and when you're writing up the exam. Okay, so there we go. There's, so I got a little note here to remind me. So I tell you that we're going to discuss these problems. They only pertain to Friedel-Crafts reactions. The other 6 EAS, electrophilic aromatic substitution reactions, they don't suffer these same limitations. So as we go up here, we got these Friedel-Crafts reactions boxed in. They are the ones that have limitations. The other 6 don't. So you have to keep them separate in your mind. Okay, so what are these limitations? Well, the first one is, if you think about the name, you would see that, oh, okay, that makes sense. The name is Friedel-Crafts alkylation, Friedel-Crafts acylation. So alkylation means we're putting an alkyl group on the ring. Acylation is we're putting this keto group, the ketone group on there. So you can't have a halide on a benzene ring, which is classified as an aryl halide. You can't have a halide on a alkene group or a vinyl group. That's a vinyl halide. They just don't fit the pattern. It's alkanes with halides and acid chlorides. Those are the 2 reagents. Other reagents of halides don't work, right? So here's a couple examples, right? So if you had chlorobenzene and aluminum chloride, you're trying to do a Friedel-Crafts reactions, you go in the lab, it doesn't work. That's because this is not an alkane and it's not a acid chloride. Same is true with this vinyl chloride here. So if your halide is connected to an sp2 hybridized carbon, gosh, that's not true. This is sp2. So let's say it a different way. If the halide's connected to benzene or to an alkene, it doesn't work. It's not a reagent for Friedel-Crafts. I got this in parentheses. So that's the bottom line. That's what you need to know. Some students are like, well, wait, what's the reason for that? If I know the reason, that'll help me remember this concept. Okay, the concept is that in Friedel-Crafts reactions, let's start off with alkylation right here. What happens is the catalyst, aluminum chloride, has an empty p orbital, and it can grab or attach to the lone pair on the halide. And then in a second step, this bond right here can break to form a carbocation. So essentially, aluminum chloride rips the halide off of the carbon, and you create a carbocation, very reactive and unstable molecule. That's what needs to happen here. And aluminum chloride just doesn't have enough oomph, enough strength to pull the halide off of an sp2 hybridized carbon. In a previous, is it later? No, it's down here. At the end of this video, we'll talk about why aluminum chloride can pull the chlorine off an acid chloride. It's because the resulting carbocation is resonance stabilized. So it's an exception. But here we go. You can't put a chlorine on benzene, can't put a chlorine on an alkane and expect it to do Friedel-Crafts. It won't work. And the reason why, those carbocations are just too unstable to form. Aluminum chloride can't make the carbocation, so you get no reaction. Ooh, well, I'm glad I talked about making carbocations because that brings us to our second limitation. If you get a carbocation, it might rearrange. So on exams, look at your molecule that you're making and decide, well, where was the carbocation? And if it was a carbocation that could rearrange to a more stable form, you have to write that product too. So here's an example, which you might see on the next exam. What are the products when benzene reacts with one chloropropane? So put the chloro group at the end of a chain of 3. Well, sure, this is the expected outcome. The pattern is wherever the chlorine's attached, that's a carbon that should attach to the benzene ring, right? So we substitute out this chlorine and we put in the benzene ring. That's our expected product. But in the mechanism, aluminum chloride pulls the chlorine off and creates this carbocation, which is primary. Remember how to do that? One way to do it, one way to classify the carbocation is to talk to the carbon. The carbon that bears a positive charge is right here, and you say, hey, carbon, how many carbon atoms are you attached to? And this carbon says, I'm attached to 1 carbon, therefore I'm primary. And then do you remember your order of carbocation stability? CC plus carbocation stability. Remember we said tertiary is the most stable, and then secondary, and then primary, and then methyl. And then we said aryl plus charge on the benzene ring, or vinyl plus charge on an alkene. They're incredibly unstable, which is why they don't form. And then out here, if we had resonance, so if you have a plus charge next door to an alkene, then there's resonance stabilization. And that's just as stable as tertiary or more so. And same is true with a benzyl. Gosh, more names. This is an allyl carbocation. Allyl, when you have 3 carbons, like 3 L's, 3 carbons, and the plus charge is on the carbon that's not an alkene, not a carbon-carbon double bond. And then if you have 7 carbons, that's a benzyl group. Remember from naming? Yeah, naming carbon. Naming molecules containing benzene. This is a benzyl carbocation. And then the plus charge is free to go all about the ring. So I'll draw the second one, and there are more, right? To draw the next resonance structure, just roll this double bond towards the plus charge. So put it there. So instead of between these 2 carbons, it's now across those 2. To get all the carbocations, all the resonance structures, move 1 pi bond at a time. So I'm gonna leave those 2 pi bonds in the same spot. And now this is the carbon that only makes 3 bonds. So the plus charge is on this top carbon. And then it can move around the ring. There's 2 more. Anyways, bottom line. Remember your carbocation stability. If the carbocation you're making is primary, look and see if the next carbon over is secondary or tertiary, because it'll rearrange. So that's what happens. It doesn't always rearrange. It's all about kinetics. So in the round bottom flask, in the lab, when you mix aluminum chloride with this halide, the carbocation forms, and if benzene's right there, boom, it attaches and it will make some of this product. But if benzene's not right there, and there's a little delay, then the carbocation says, whoa, this plus charge on a primary carbon is bad. Hey, why don't we do a hydride shift? This hydrogen with its bonding electron slides over to connect to the end, and now the carbon in the middle only has 3 bonds. That makes a secondary carbocation. And if that forms, then when the secondary carbocation attacks the benzene ring, it attaches where the plus charge is, where the carbon is needing a bond. So it's going to connect there and make isopropyl benzene. So you get 2 products on exams. You must draw all the products that result in the reaction. And the products will be without a rearrangement and those that are with a rearrangement. And you can sometimes get more than 1 rearrangement. Okay, that's a bad one. we don't like carbocations. Okay, so Friedel-Crafts alkylation. Watch out for carbocation rearrangements. A nice rule of thumb is before you start predicting products, look at your reagents and ask, what degree are you, chlorine? Well, chlorine's shy, so talk to the carbon. Hey, carbon, what degree are you? It looks around. This carbon's only attached to one carbon. This is a primary halide. Ooh, I wish it was tertiary. Tertiary halides should not rearrange when they form carbocations, but secondary halides and primary halides create secondary cations and primary cations, and they can rearrange. All right, done with one of the worst ones here. Third one, this one's not too bad, you just have to remember. And it won't make that sense now until your next video, but bear with me. Limitation number 3 is if the ring, the benzene ring is too deactivated, Friedel-Crafts reactions shut down. So in our next video, we'll talk about what happens if there's already another group on the benzene ring. How does the presence of this nitro group on benzene affect its reactivity? And it turns out groups on the ring have a big effect. Some of them like make benzene even more stable to the point where it's so stable it doesn't even do Friedel-Crafts reactions. We call such groups, like a nitro group, it stabilizes the ring, but it shuts it down. The ring doesn't want to do a reaction. And so remember these reagents? Those are the exact same reagents we had right here. If you take pure benzene, methyl chloride, aluminum chloride, it works. It makes toluene. Yeah, remember your common names. And that works just fine. But what happens if you start with nitrobenzene? If you start with a nitro group already on the ring, there's no reaction. In fact, you can use nitrobenzene. It's a liquid at room temperature. You can use it as a solvent for Friedel-Crafts reactions because nitrobenzene won't react. Put in another molecule that contains a benzene ring, and that's where you can do a Friedel-Crafts reactions on. Okay, so next video, we'll watch for a listing of deactivating groups, strongly deactivating groups. And anytime those groups are on the ring, we'll have to remember, Friedel-Crafts won't work. More about that in the next video. Ooh, but it's only Friedel-Crafts, right? So gotta keep these separate. If you got the nitro group on benzene and you don't do Friedel-Crafts, you do one of the other 6, it's slow, but it still works. The sulfonic acid group, right? The reagents say what goes on the ring. These reagents say, hey, put SO3H on the ring. And the nitro group says how fast. It's going to go slow because it's a deactivating group. It also says where. That's the topic of our next video. So let's not get ahead of ourselves. For now, just know that Friedel-Crafts has a problem. If there's a strongly deactivating group on the benzene ring, it doesn't work. The other end of the spectrum comes up in limitation number 4. Amines turn out to be powerful activating groups. They destabilize the benzene ring, makes it want to be more reactive. And it turns out the amines, they're so reactive, why don't they work in Friedel-Crafts? Well, they're so reactive, they actually react directly with the catalyst and shut it down. So if you have an amine on benzene, or actually the amines anywhere else, the amine will attack the aluminum and connect to it. And now if the aluminum's tied up making a bond to nitrogen, the aluminum's not available to go attack methyl chloride or any other halide you have there. Doesn't work. So we'll have to remember if there's an amine and the nitrogen must have a lone pair, that's all you need. Nitrogen with a lone pair, it could be NH2. It could be dimethylamine, 2 methyl groups. It could have 1 methyl. It could have any set of carbons. We're watching for a nitrogen with a lone pair. That lone pair will then react with aluminum chloride, and no reaction for Friedel-Crafts alkylation or Friedel-Crafts acylation. Started. Last limitation, number 5. We'll discuss this more in the next video too. It turns out polyalkylation can occur. Poly means many. So alkylation means add an alkyl group. Polyalkylation means add multiple alkyl group. So hey, we're expecting this reaction to happen cleanly. It's not very clean. Take benzene, methyl chloride, and aluminum chloride. Yes, Friedel-Crafts reaction works. Get toluene. Awesome. But during the reaction, the product reacts. So before the reaction is all done, some of your product that you're starting to make will then go and react with the reagent. So now the product you just made, it's not just going to be inert and staying off to the side, one side of the beaker. No, it's mixed in there. It sees the reagent. And it turns out the methyl group weakly activates the ring, makes it more reactive than pure benzene. And so now this is more reactive than the starting material. So it reacts again to create this product and that product. And guess what? If one methyl group activates a ring, two methyl groups are going to make even more reactive, make it more reactive. And so now these molecules react with the reagent and you get a third methyl group and so on. So dang it. Okay, so we'll discuss this problem in the next video. But just to kind of alleviate any worries right now, it's like Friedel-Crafts, you got 5 problems. I'm just going to avoid them. You can't. Friedel-Crafts turns out to be the most popular of these electrophilic aromatic substitution reactions. It's very useful to put carbon on a ring. So you just have to commit these 5 to memory. And for the most part, you can just ignore number 5. In the lab, what you do to minimize the problem from number 5 is you use an excess of benzene or excess of your starting material, and you stop the reaction early. So on exams, if I say, hey, predict the product of this reaction, and that's all I say, the reaction says, hey, whoops, let's not get a rearrangement happening. Let's just do ethyl. There you go. No, this is a primary halide, and that's a primary carbon. There's no rearrangement here that will help stabilize the carbocation. Okay, if I say predict products, or how about predict all products? I will give you full credit if you only give me this structure. Because in the lab, you can make this the major product. You can actually say, let's use 10 moles of this and only use 1 mole of this. Do I need a mole of this aluminum chloride? No, it's a catalyst. Trick question. So use, I don't know, 0.001 moles of the catalyst. And it turns out all of this will react. You'll get 1 mole of this, and then you'll have 9 moles of benzene left over. But some of this may actually start reacting with this along the way. You might get some trace amounts of the polyalkylation products, or more than one ethyl group adds to the ring. I'm talking too much. So polyalkylation, I need you to know about it. There might be a specific question addressing polyalkylation. You'll see that in the homework. You'll say, how come there's more than one product forming when benzene reacts with methyl chloride? Why is there one more product? Oh, it's polyalkylation. And it might be asking for a mechanism or some verbal explanation. And the verbal explanation is the product has an activating group. The product is more reactive than the starting material. So the product reacts again to make more products. And then if I ask you to just predict the product, I'm not expecting you to report polyalkylation. It's just going to get too messy. So we'll just say, okay, predict the product of this reaction. This is a tertiary halide, so it's not going to rearrange. Yay. And then what's the product? We're not going to worry about polyalkylation. We'll just say that's the major product. Cool. Okay, we talked about all the limitations for Friedel-Crafts alkylation. Well, the ones that make sense also apply to Friedel-Crafts acylation. What do I mean by make sense? Man, this is a mess. Okay, let's scroll over and get a little bit of room over here. Move this out of the way. Okay. Acylation, that's where you start with benzene and you add an acid chloride. And it can be anything, right? Okay. So now let's see. First limitation was aryl halides and vinyl halides don't react. Well, yeah, this is not an aryl halide. It's not a vinyl halide. It doesn't make any sense. So don't worry about this first one for Friedel-Crafts acylation. Can I just say FC acylation? That's because you use an acid chloride. Okay, second one, carbocation rearrangements. Okay, it turns out, no, you don't have to worry about that for acylation either. That's because here's the mechanism which is not required for exams, yay. Aluminum chloride is going to pull the chlorine off, and here's its two-step mechanism. Lone pair of the chlorine of the acid chloride connects to the empty orbital of aluminum, makes this complex, and then this bond breaks to form this intermediate, aluminum with 4 chlorines. That creates a plus charge on this carbon here. And now what can happen is a lone pair from oxygen can come down to make a triple bond and put the plus charge on the oxygen. And now that those are 2 resonance structures. So we got 2 good things happening. One, 2 atoms bear the positive charge. Sometimes it's carbon, sometimes it's oxygen, it's sharing. The second thing going for it is you've actually made an additional bond. Bonds are stabilizing, right? A double bond's more stable than a single bond. Triple bonds are more stable than double bonds. So a triple bond here makes this intermediate, this this cation more stable. And so you don't see rearrangements with acylation, because if you had a rearrangement, you may not be able to get this resonance structure if the plus charge on carbon moves down the chain. Okay, yay. So Friedel-Crafts acylation, the first limitation doesn't apply. Second limitation, rearrangements, doesn't apply. Third one, that still applies. So if you had nitrobenzene again, maybe I'll draw it this way, and you tried to do an acylation reaction on it, there's no reaction. So I could put this on the exam. I say, hey, predict the product. You could just write N.R. or you could write the words no reaction. Don't leave it blank. I won't know that's what you mean. Put something there that says, sorry, that won't work because this is too deactivated. This group deactivates ring. Doesn't work. Okay, fourth limitation. Yeah, if you have an aromatic amine, so we had NH, and there's an ethyl group here. That's an amine on benzene, and I try to do the acylation reaction with aluminum chloride, it's no reaction again. So this one makes sense for Friedel-Crafts acylation. Yep, it's an amine, try to acylate it, no reaction again. Polyalkylation, no, there's no number 5 here. Why not? Well, what's the product of acylation? So I'm going to use this acid chloride with the terp-butyl group on it. So you get benzene, and the point of connection where the halide is, that's where the group connects to the benzene ring. That's a ketone. We're going to learn in the next video that ketones are strong deactivating groups, just like the nitro group. So if this is too deactivated to react, there's no reaction on it. This is the product, and it can't go and do another reaction. Unlike this one over here, when you add a methyl group to benzene to get toluene, the methyl group is activating, and now the product can react and reacts faster than benzene. Not true for acylation. Yay, there is no polyalkylation. Actually, from the word, that kind of makes sense. Polyalkylation, Friedel-Crafts alkylation. Yeah, that's a problem for Friedel-Crafts alkylation, but this is Friedel-Crafts acylation. You don't have to worry about polyalkylation. Doesn't apply. Okay, hope that makes sense. Get some practice in the homework. I'll see you in the next video.